Hello everyone, so today I would like to present my project result where the title is Effect of Ply Orientation and Laminate Sequence on Composite Pressure Vessel using NCS ACP. So the study focused on the composite pressure vessel, which are lighter than metallic pressure vessel, and for the composite itself is anisotropic material where the properties depend on the fiber directions and the ply angle. Different ply angles carry different loads. Uh, for example, 0-degree plies support axial load, and for 90-degree plies support hoop load, and for 45-degree improve shear resistance. Therefore, laminate stacking sequence is important because it affects stiffness, deformation, stress distribution, and failure index. This study evaluates how different ply orientations and stacking sequence affect total deformation and Chaiwu failure index. Since the performance of the composite pressure vessel depends on the laminate arrangement, the model assumes the model and assumption must be clarified defined. And in this study, 90-degree symmetry cell model was used to reduce the computational cost while still representing the full vessel behavior. And the model was analyzed using NC static structural and ACP, and the composite material was assumed be orthotropic. And internal pressure was applied to the facial. Since only 1/4 of the model was used, symmetry displacement constraints were applied on the cut edge. One edge was constrained in Y directions, and the other edge was constrained in the Z direction, while the axial direction was left free to allow natural deformation under pressure. This setup represents the full pressure vessel behavior with fewer elements and shorter simulation time. Since the composite behavior depends strongly on the material direction, the material properties and laminate sequence were defined in NCS ACP. The material used in the study is epoxy carbon unidirectional prepack, which is an orthotropic composite material, and its stiffness is much higher in fiber direction with E1 equal to 200, around 200 GPa, while E2 only 10 GPa. And also 3 laminate stacking sequence were compared, so all cases use the same material, same number of plies, same ply thickness, which is 0.8, and same total thickness, where the total thickness will be 6.4 millimeter. Therefore, the comparison focus only on the effect of the ply orientation and stacking sequence on deformation and Chaiyu failure index. A mesh convergence study was performed to ensure the result. 3 cell element types were tested, and the mesh size was refined from 15 millimeter to 1 millimeter. Total deformations and Chaiyu failure index were used as the convergence parameters. And case 1 was used as the baseline laminate configuration, so only the mesh type and mesh size were changed. The result was considered converged when the percentage change between two consecutive mesh size was less than 5%. Since mesh quality affect both deformation and failure predictions, the 8-node quadrilateral cells show the most stable Chaiyu index from 2 mm to 1 mm mesh size. It showed the total deformation changed by only 0.288% and the Chaiyu failure index changed by 1.57%. Since both values are below 5% convergence criterion, the node quadrilateral cell with 1 mm mesh size was selected for the laminate comparison. So the same mesh setting was applied to all laminate case for fair comparisons. This slide compares the total deformation of the three stacking sequence. Case 1 gives the lowest deformation with maximum deformation value, while case 2 gives the highest deformation. And both cases show maximum deformation near the dome section. And for the case 3 has deformation of 1.788 millimeter, but the maximum deformation shift to the cylindrical section. These results show the play orientation and stacking sequence affect not only the deformation magnitude, but also the location of maximum deformation. And the deformation results show the global stiffness of the facial, but it doesn't indicate whether its composite layer is safe. Therefore, the Chaiwu failure index was evaluated to identify the critical place. In this graph, the red line represents failure index equal to 1, which is it is the limit for the failure. So for the case 1 shows the lowest failure risk because only the last play exceeds this limit. And case 2 has two critical plays, play 4 and play 5, while the case 3 is the most critical because several layers exceed the failure limit. Overall, case 1 gives the best failure performance, but further improvement is still needed because one play still exceed the limit, even small number. And then to identify the failure location, the Chaiwu result was observed layer by layer, starting from the case 1. Most layers show relatively low failure index value. However, the last ply becomes the critical layer because it exceeds the failure limits. And the contour results show the failure risk is concentrated near the center of the dome area. Therefore, for the case 1 give the best performance among the three cases, but the laminate is not fully safe yet because only one ply still exceeds the failure limit. And compared with the case 1, case 2 shows higher failure risk because ply 4 and ply 5 exceed the failure limit, and both plies are 90-degree plies, which are related to the hoop directions, and the contours show that the high failure index is concentrated around the boss and the dome area. And for the case 3 show the highest failure risk because several layers exceed the failure limits. Since the sequence doesn't include 90-degree hoop plies, the laminate has lower resistance to hoop expansions. Therefore, case 3 is the least favorable sequence. And for the conclusions, the 8-node quadrilateral cell with 1 mm mesh was selected due to the stable convergence in both total deformation and Chaiwu failure index. And the second one is the laminate sequence affect both deformation pattern and Chaiwu failure index. For case 1 and case 2 show the maximum deformation at the dome, while case 3 showed maximum deformation at the cylindrical section. And case 1 had the best failure performance with only the last play exceeding the failure limit. For the case 3 was the most critical because many layers exceed the failure limit. For overall case 1 is the most favorable sequence, but further improvement is still needed. And for the future improvements, I will improve the laminate sequence to reduce the Chaiwu failure index below 1 for all plies, and modify the critical ply orientation, especially the last ply for the case 1, and evaluate the additional stacking sequence and ply thickness combinations, and also consider the optimization to reduce deformation while maintaining safe failure index. So that's all for me. Thank you.